Why would you do all that?
Well, I mean, you could. All right, that's the most direct way to do this. You could say x is u, y is v. Now let me do one thing to this. Let me get you guys off of that. Here, do that. So x could be u, y would be v, and then z would just be u squared plus 2v squared. Now, have you tried to graph in your graphing calculators? Have you ever tried to graph a complete circle by doing the top and the bottom halves?
Yes.
Do you ever notice that, unless you have one of the really, really fancy ones with a lot of computation, it never meets at the ends? If you did that on a normal graphing thing and you try to graph a sphere, it would have places on the edges where it wouldn't meet. Because think about it, when you get to the edge, the step size you have to be able to catch that whole edge is stupid small. I don't know if you guys understand what I'm saying. So as I'm moving here, I can make a big step size and still catch it. When I get over here, how much is x actually moving at the edge? Barely at all. It's got a lot still to capture. That's why it can't quite do it. It's beyond its resolution. But if you use parameters to define it instead, then the computer systems have no problem getting it to hook up because it's using a natural coordinate system, not this XY system that's not going to work with that. Maybe you guys get that. And they have a picture of that on page 1154 if you want to see that. Okay, here, this is really kind of cool. I'm going to show you something on the computer there. I'll show you two things here. Maybe someday. While that thing is warming up, let me throw one more idea at you. Oh, there it is. Let me not throw another idea at you. So here's a couple examples of the grid lines I'm talking about. So with the sphere, we're used to the grid lines already. We call the grid lines on a sphere, we call them, like on the sphere that we live on, we call the grid lines what? I don't know if you guys remember. These are latitude because they make a ladder, and these are longitude because they're long this way. All right. So this is an example of the. These are the grid lines on the surface of the sphere. Now they have some other shapes. That's an inch shape. I can turn that bad boy too. So this orange is the U. So if you let V be constants, you would get these lines. These would be the curves. These would be the C's. If I let V be constant, the equation of this would come up with a curve, the normal curve we're used to, right? Like you integrate over a curve. But if I put all of those orange lines together, it creates this surface. Okay. And I can do the same thing with the blue. In the blue, every single blue line, if I let U be constant and V vary, I'm going to get those as grid lines, just like the X and Y-axis are the basic grid line. And then you can draw more grid lines parallel to those to find stuff. So this is kind of nifty. This is choosing your coordinate system based on how the surface itself moves. And that makes more sense than trying to force every surface to work with X, Y, Z, or even work with spherical. This just changes it on the fly. So that's kind of crazy. Every single surface has its own coordinate system in a way, right? And here's something even cooler. This is one I got to remember to send out to you guys. It's one of the best little parametric graphers I've found. This looks really funkadelic. All right. So this is in the book actually. This is page. This is figure 5 on page 1152. I'm not sure exactly what scale they use, but oh I don't know if you can see it really well, but I mean, up here you can plug in x, y, z in terms of u and v. So you can make it whatever the hell you want to. You can control the u and v, max and min, the opacity, whatever. But what's really kind of nifty about this that I didn't notice at first is it does show you the grid lines. Here's the grid lines this way, here's the grid lines this way. You guys see what I'm talking about? Grid lines. That's kind of awesome. Alright, maybe it's just me. I don't know. But you can make these whatever the hell you want to. So let me show you something that's really kind of nifty. So I mean, you could just play around with this shit. I got to remember to send this out to you. Hopefully, some of you guys are not quite as nerdy as me, but sort of in that direction. I remember just when I first learned how to do stuff on the graphing calc, I just started throwing shit in there and saying, "Look at that shit! Holy shit! What the shit?" This thing, it's great. And let me show you something that's really going to be nifty. Do you remember one of the things you hated the most in 180 was at the very, very end of the semester? What was it at the very end of the semester in 180 you guys did? Yeah! Surfaces of revolution, right? Yeah. All right. So now watch this. This is kind of neat. I'm just going to show this to you because I'm not going to... So if I have some... let's do this. If I have some y equals f of x, and I want to rotate that bad boy, right? I let x be x, and then I make y equal to f of x sine theta, and I make z, well, let's make it cosine. Y and z are sort of going to be like x and y, offset. Obviously it would work if you didn't do this. I don't want to agree with the book. You can take any function you can think of. So the one the book does is interesting enough. It's the sine. So if up there I put in there, let x be u, let y be sine u. It's a little bit touchy when you got to put the stuff in parentheses in the sine. You guys with me? It's a little bit touchy about that. You can't even see it, so it doesn't matter. You guys see I'm just following that format. Sine u times cosine v. So in this case, u is x and v is theta. You guys see how those two would be the parameters here. And then the last one, z, would be sine u times sine v. Does it match up yet? Let's see. There you go. So you just get the sine function rotated. Isn't that nice? And you might be able to imagine that maybe some of the calculus you have to do is actually easier if you use more parameters to show it. So then you could do, you could, whatever you put here. If you put here, what was the neat one? E to the negative u squared. That should work.
How did you get sine u originally?
That's going to be the function that I picked. Whatever function I want. So if I want sine x and I want to rotate that, I put it here and here. So now I want to rotate e to the negative u squared, or e to the negative x squared. That's nifty. And, then you can play around with it. I mean, it's really kind of nifty. It really is. So that in itself is cool. That the idea of how to build a set of functions that would take a function in xy plane and rotate it for us. That's what these do. Okay, I like it. So these are, I just constructed a surface. So anything that we're about to do with surfaces, I could do with this. Right? Which is really doing something with this that we did in 180 the weird way, like turning things and saying, do you use a washer, do you use a disc, what's your inner radius, and all kind of shit. Okay, I like it. Oh, so now that we got this idea of surfaces, the very next thing we want to do to build off of surfaces is how do we find a tangent plane to some parametrically defined surface, right? So we know how to find tangent planes when the surface is defined the way we did before. What would happen now? So if I have find a tangent plane this is where section 59 is going to come back in an interesting way. This is also why I ended up not being too concerned that I had to make that extra credit. Let me see here. Where do I got this? Oh, okay. So the point P naught has position vector R UV. Let's make it U naught V naught. So it matches up with the P naught. So P naught is on the surface, and the position vector for that is R of U naught V naught. So U naught and V naught are the values that get me to that point on the surface. And I want to find the tangent plane at that point. I like it. Now, how did we do it before? What was it built off of before? You guys think about it for a second. What does it have to be built off to find a tangent plane, which is really just the idea of a tangent line taken to the next dimension? So what did we find? What do you have to find for the tangent line? You have to find the slope. So what did we do when we had a function of multivariables? We have to find all the slopes. Well, not all of them, but the two main ones. Fx and Fy. Well, what's acting like x and y now? U and v. I love it. So we're going to have to find like Ru and Rv. So Ru, there's a lot of stupid jokes that can come after that. Ru would be letting v stay constant, so it would be related to, it would be tangent to the, parallel to the U grid lines. You guys with me? Okay, I like it. Let's see what I say. Blah, blah, blah. Yeah. So Ru would be. Oh, that's easy. Ru would just be dx du, dy du. Make that a lot clearer. dz du.
Okay. Can you see that? Like, no? I mean, like, now with the formula, I'm sure with the function line, it just...
Oh, yeah. Let me get all this out, and then we'll do it next area. Yeah. Rv would be similar to that, just in terms of v, right? Same thing. dv, blah, blah, blah. Now, here's where things get interesting, as if they're not interesting enough already. You see, if you guys... So if we go back even further, what did we do once we found two vectors in a plane? To find the equation of the plane, what did we do with those two vectors? Took a cross product, because that would define a normal curve, right? A normal vector to that plane. This is what should look familiar to those of you who did section 59. And right here, when we say this, if Ru cross Rv is not 0, this is called smooth. The surface is smooth, at least near this point. If it's never 0, then it's just smooth everywhere. If that equals 0, there could be a weird cusp there or something where there would be no tangent plane, really, right? So obviously we want to find this cross product. And the nice thing is, Ru cross Rv, okay, is going to equal the ABC from before, the same ABC. Remember the normal vector to ABC? You guys with me? Why does that make sense? Because the two vectors in the vector plane, when we did the definition, if we found the equation of a plane, did the two vectors we used, did they have to be orthogonal? They did not have to be orthogonal, if you remember. I gave you just 3 points in a plane. Did they have to make 90-degree angles, any of them with each other? No. You just got one vector, got another vector, cross them, and of course, it doesn't matter like this, right? It's going to all have the same normal vector. I like it. So that's really what's happening. We have U and V that aren't orthogonal to each other necessarily. I like it. close to this point, it is going to be flat because it is a smooth surface, we're assuming. I like it. So then basically close to that point, it is a little plane already. It's a little patch of a plane. So if I take the cross product of these, I get the normal at that point. And then I can just construct good old ax plus by, you know. Ax minus x naught plus b blah, blah, blah. Good old equation of a plane. Let's do an example. Let's see. So the really important things here are these two things to be found. This is the part that should look familiar. Those of you that did 15.9, what would be the next step here to figure out your multiplier to make the transformation stuff work for your intervals? Who did 15.9? What do you do with this? You take the magnitude of this, right? Wouldn't that give you the multiplier? So it would give you rho squared sine phi, for example, if you did spherical coordinates here. Okay, I like it. Blah, 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 blah. So let's do this example. Let me give it to you in this form here. Because I think part of the problem might be from here to here. But remember, this is all in 3 dimensions. We're in 3 dimensions right now. So this has got an I hat, j hat, k hat. It's got x, y, z components. That's where these come from. So if I give it to you like this, you can identify x, y, and z. So that's what it's given like that. So x is u squared, y is v squared, z is u plus 2v. Should work better. A little bit. So what's RU? RU. Yeah, you can make your own jokes up there. It's my beautiful grammar when I did U subfront. What is U? What does U mean? Right? What is RU? 2U. 0?
2B.
1. With 2 U's. No, 2 U. All right, there. I like that. Because if you haven't seen the movie, see it. RV. 0. 2B or not 2B? 2. That'd beat you guys to it. Now this is the way I do cross products. I just write the vectors out, and then you've got your bam, bam. Right, so what would RU cross RV be? It would be 0 minus 2V, and it would be minus 4U, and then it would be 4UV. So whatever way you find cross products, do that. That's really the way I do it, to be honest. Hopefully it came out right. Did it come out right too? Yeah, good. All right. So now I'm ready. I can find the tangent plane at any point on this surface. So I want it at the point 1, 1, 3. Oops. So in this case, what's nice is that means that U is 1, V is 1, and Z is 3, right? I mean, that's so nice. You can see how it works, right? You guys see? So it depends on the way this is defined. If they give you the X, Y, Z point, but everything you're doing is in terms of U and V, you've got to be a little careful there. So what is the value of this cross product at that point? Yeah, -2, -4. 4, right? That's your ABC. So then it would be, the tangent plane then would be, good? -2, x minus 1, minus 4, y minus 1 plus 4 z minus 3 equals 0, and then you can do whatever you want to after that. I like it. What's up?
At 113.
Oh yeah, so I got to tell you this. So the very first thing I did was I just got the general thing for any point. So I can find the change in plane at any point now. Right? This is basically going to be the slope in a way. That's the normal vector for any point. So I want to know at the point 113. Right? So a problem in the book would say, find the tangent plane to this surface at the point 113. So you would find this, you plug that in, you get the specific stuff at that point, and that's the normal vector, so it's just the coefficients, right? The ABC coefficients.
So are you letting x equal u?
Well, that's right here. This was given to me. So at the point 1, what's u? 1. 1, v would be 1. I like it. And z, u plus 2v is 3, so that works, that checks, right? Okay, I like it, I like it, I like it, I like it. Okay, yes?
How'd you get RV again?
Just took the derivative partial with respect to v. Keep u constant. So that's 0, 2v, 2. I like it. So it's just like fx, fy, ru, rv. Just u and v are now the variables. One's going to be constant. Same exact stuff. I like it. Yes?
So now that is a normal vector, just with it's a parametric normal vector, essentially?
Yes. Yes.
Okay,
The nice thing is...
I've gotten it completely, so.
All right. Well, no, I'm not expecting you to get it completely like that.
Light bulb is
Starting to turn on. That's good. There's a slight amount of electricity. The dimmer switch is going up. Let me see. Do I want to do this example? Blah, 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 blah. No. Yeah, let's do this. Here we go. Yeah, cool. I just want to show you, just in case you did 15.9, I want to show you two things here. First off, here's you've done this so much over the years in calculus, Calc 1, Calc 2, Calc 3. When you see a picture like this, you should know what it's headed towards. Hopefully, right? What does this look like it's headed towards? The idea, what's going to be used here in a minute? Integration. This looks like it's Riemann squares here, right? The squares that we built. And we're going to integrate this over the whole area to get the surface area. Yes. You can see this little delta U, delta V. This is their UV plane. So I could make a t-axis. If t goes from 0 to 7, I'm like, here's my t-axis 0 and 7, and that doesn't do shit for me. This does a little bit. I mean, there's the UV plane. That's what U and V do. But what does the actual thing end up looking like? Over there. So those are the behind-the-scenes controllers, the U and V. And that's, of course, what it ends up looking like. If I get this little, what we call patch, and I just add up all the patches. Now, hopefully it makes sense. It's going to involve, there's my little dA, right? Delta U, delta V. Oh, poor little dude. Delta delta U, delta V. Now there's this little dude. This little piece. Let me see. Remember, now what was the area? I mean, they give it to you right there. What was the area of a parallelogram? That's when we first learned. Yeah, and the cross product, magnitude of the cross product directly relates to the area of the parallelogram for which those inner things are the vector side pieces, right? So when I do RU cross RV, I'm getting the area of that little parallelogram. So if I add up all those little parallelograms, and of course, why is it a parallelogram when really it's curved? The U and V axes are not straight. But of course, like I said earlier, we are in the limit where things are getting very small. So this is kind of a huge piece. The smaller of a piece I look at, the more linear these sides are going to be, because we're assuming it to be a smooth surface. It's got to be a smooth surface for this to work. I like it. Beautiful, beautiful. It's not that big of a step from what you've done before, to be honest. So obviously that's going to lead directly into your integral. It's going to look like this here. Now I want you to realize something. Just to kind of look ahead real quick. Let me see. I think I put this in my little notes. Blah, 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 blah. No. Okay, yep. Where are you at? Probably over here. Yes. So this is just to get, if you have a surface defined parametrically with U and V, which we just saw a lot of ways you can do that. You can make shit up and see what it looks like. To get the area of that surface you just created, you do this. Okay. Can you imagine? So what, recall this, what did this line integral, what did this do for us if I do this? Actually, let me even go back further than that. How far back did I want to go? There you go. If I just do this, if I just do integral a to b dt, what would that do? It would just be a length, right? Now, if I plug stuff in here, like if I do this weirdness. If I do this, arc like, and there's a 1 here, right? So that idea keeps coming up about this whole piece of it is really just related to ds, if you remember. So if I integrate r prime t dt, I can end up with an arc length. Now if I put something here instead of 1, if I put a function here, that's going to be our normal line integral evaluated f along it. That's going to be, one way to look at it is the area of a curtain, because f would be the height of the curtain at every point, every t point. So imagine what's happening here. This is the area of a surface. This is the length of a line, right? If I put something here that's not 1, I'm going to get the area of a curtain or the accumulation of that function along that line. So if I put something here instead of 1, it's going to be what we call a surface integral. So instead of just doing the integral along a line, I'm going to do an integral across the surface. Now those of you taking any physics, we're getting closer and closer to stuff you might have already seen. The next thing you talk about is integral through a surface of a vector field. That's related to Gauss's law. Gauss's law. Yeah, dude. Yeah. If you haven't taken physics, don't worry. You don't suddenly have to learn that. Let's see, what did I skip over now? Blah, blah, blah. Oh, so please, did we do an example of this just now about how to get this? Yes. Couldn't I find the area of the surface of that surface? Couldn't I find it if I give myself some endpoints for U and V? Couldn't I do that here? Yes. I just have to get the length of that RU cross RV, throw it in there, and do it. You guys with me? So that's not that big of a step. And if I throw a function in there, that would actually be the next section. Okay, so let's take it back a step. Just a couple more things I want to say. I think, well, I'll tell you before you leave. Bye, John. No, you can. You're okay, man. You told me you had to leave earlier. Yeah. I like you. John's such honest dude. Oh. If my surface is actually a function of x and y. So we've already seen surfaces. We've had a lot of surfaces we talked about, and they've all been functions of x and y. This u and v thing is something new. But I can always take the formulation of what I'm doing and take it back to what we had before. If I did have a functionally defined surface like this, then let's see, what can I say here? X equals x, y equals y, z equals f of x, y. That's amazing. What would Rx be? 1, 0. Partial f x, I like it. Ry would be something very similar. 0, 1, partial fy. So what would Rx cross Ry be? Minus fx. Minus fy. 1. I mean, I'm doing this, but specifically for the case where my surface is defined in terms of x and y already. It's the normal surface we worked with before. So what you end up with is something that should itself look very familiar. Actually, this whole section is rife with deja vu moments. Let's see if you guys have that moment here. And then Rx cross Ry, length of it would just be square root of... Yeah, let me write it like this. dz dx squared partial d dy squared plus 1. That should look sort of related to something we've seen before. So then the area of the surface would just be this in there. What do I want to say? dA. Now remember, the length of some arc, way back, actually did this back in 180, I think. I think we talked about it before in here. It was just that. Is it dA, Jeff? No. D. Oh, I can't remember now. What would it be? D, whatever. Yeah. But I mean, this look, it just added that extra dimension in. We've seen that happen a lot. It's kind of nice that sort of happens. It keeps the idea from before and it just makes it larger. Pythagorean Theorem is the nicest example of that, which is really what this is. Let's do a real quick example of this. By the way, let me just say this right now. This is what I was going to say. Poor John.
It's all right, it's on camera.
I'm going to make 16.6. You have to do 16.6. But I'm going to make 16.7 extra credit. One more slab of extra credit for you.
66 though.
All right, that doesn't mean I'm done. Just want to say that right now before I forget. Yeah. Oh, it should be dx here, right?
No, I meant
dy? Oh, dz.
Oh,
dz, yeah. That was z equals f of xy. Yeah, partial. Blah, 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 blah. Oh, how about this? Example 11. Was it under?
This is example 1, you said.
Yeah, it's example 11.
Not right. Right.
So this equals 9, yeah. So do you guys see that this is describing a surface, right? A paraboloid itself is a surface, it's just infinite. Right? It kind of sucks. So I want the part of this paraboloid that's under z equals 9. So it's not the volume between those two surfaces, it's the area of this paraboloid, the surface itself, not the volume. So I've got, in terms of z, I've got this, so I can use the one we just talked about, right? I like it. So then, what am I going to let, so for example, x is x, y is y, z is x squared plus y squared. So the area is going to be the integral. We got to figure out the limits. Square root of dz dx. So what's dz dx? 2x squared, so 4x squared. dz dy, same thing. So it'll be 4y squared. Is everybody cool with that because I'm squaring it? Right? Good old Pythagorean rule. Plus 1. Oh, where'd it go? dA. Now, obviously, I desperately want you to realize, if you've been doing the homework, you realize that sometimes you fall back on changing coordinate systems. You can do that anytime you want to. We currently have the XY coordinate system. Is that the way you want to do this square root with multiple variables in it? Shit, no, right? So obviously I want to change to polar. I like it, because I'm really only in 2 dimensions here, right? So this is going to look like 4r squared plus 1 r. And of course that's what saves your ass here, right? Why is that r so important? Because now I can use u sub. I like it. And my limits here would be what?
0 to 3 for r.
Yeah, because z equals 9. So at the top it's going to be 9 equals x squared plus y squared.
3.
I like it. Yeah. You see. And of course theta is going to be, we want the incomplete thing like that. You're like, just shut up and put a 3. Okay. All right. I'm not even going to do that. See, I never finish examples. I mean, but if you can't do that, you don't belong here. Oh, cool. Oh. I desperately want you to realize how, if you can get 16.6, 16.7 is not that big of a push, and it's actually very similar to stuff we've done where that's not a 1, now it's a function in there that you have to do. It's very, very similar to what we had to do before. So it's a very doable thing, especially if you're somebody that needs the full vector calculus package for wherever you're going next. You want to do those 3 sections at the end of 16. You'll get some extra credit, plus you'll make sure you're ready for the next level. So you don't have to do section 16.7 homework. You don't have to do it. It's extra credit. But notice the pattern here. If you really want to think of it this way, dz dx, dz dy, so this would be dz.
Yeah.
Look.
Okay. Alright.
Yeah. Oh, yeah, practice.
You're going to post the rest of the homework?
Yeah.
So that's just my chapter.